Welcome to the Explainer. I am so glad you're here. Today, we're taking a highly precise, completely fluff-free tour of a truly critical piece of machinery, the Bombardier Q400 Auxiliary Power Unit, or APU. Now, for those of you focused on understanding exactly how this aircraft operates, we are going straight to the source. Everything you're about to hear is directly translated from the Bombardier Q400 Aircraft Operating Manual. No guesswork, just the facts. We're going to break down the complex system logic so you can walk away with a crystal clear understanding of the APU's anatomy, its safety features, and its exact operational sequences. All right, let's dive right in. Here is our flight plan. We'll be looking at the anatomy of the Q400 APU, the flight deck controls, fuel and electrical systems, the bleed air system, the automatic fire protection system, and we'll wrap up with faults and the normal shutdown procedure. Section 1. Anatomy of the Q400 APU. Let's talk physical hardware. So when the optional APU is installed, the standard composite tail cone of the Q400 is actually replaced with a titanium tail cone and firewall. If you were to look up from the bottom of that tail cone, you'd access the APU through two clamshell-type doors. Inside, you've got a gas turbine engine driving a DC starter generator. But the real brains behind all that hardware? That's the APU FADEC. That stands for Full Authority Digital Engine Control. The manual explicitly states that this digital system handles, well, everything. It automatically performs the start control, it manages normal operation, and it completely handles malfunction monitoring. It's essentially the ultimate overseer of the APU. Now, let's map out the physical airflow. Intake air is drawn through a screened inlet duct right on the right rear of the fuselage. Then, after the turbine does its thing, those exhaust gases flow through an exhaust ejector and are discharged upward at the very aft end of that titanium tail cone. Oh, and here's a great little operational detail straight from the manual. There's an optional louvered inlet cover available. It's specifically there to prevent snow and sleet from getting into the APU inlet when the airplane is sitting out on a long turnaround or remaining overnight. Pretty clever, right?
Section 2. Flight Deck Controls. How we interface with the APU.
The primary way you interact with this system is via the APU control panel up on the overhead console. But you visually monitor its status on the multifunction display, or MFD, specifically on the electrical page. And this page brilliantly shows the visual logic Bombardier uses to talk to the flight crew. In normal states, you'll see white digits. Or when it comes to generator load, if the load is exactly in the expected range, nothing is displayed at all. Basically, no news is good news. But if things shift into a warning state, the display aggressively grabs your attention. If the battery temperature hits between 50 and 65 degrees Celsius, the digits turn yellow. Exceeds 65 degrees, they instantly snap to red. Plus, a literal plus sign appears next to the load digits to explicitly warn you of a DC power source overload. It's a highly visual, color-coded safety net. Moving on to Section 3. Fuel and electrical systems, the lifeblood of the APU.
The APU gets its fuel from the left wing collector bay, where a gravity-fed, APU-driven fuel pump maintains positive pressure. But you absolutely have to know this specific limitation: 454 kilograms, or 1,000 pounds. Here's why that matters. If the fuel level in that left tank drops to roughly 454 kilograms or less, the auxiliary fuel pump in the collector bay is no longer fully submerged. And if it's not submerged, it can suck air right into the APU fuel feed line. That air leads to APU surging and ultimately an automatic shutdown. This is a critical operational threshold right out of the manual.
Let's pull back and look at the APU performance summary data. First off, notice that the rotor speed stays completely locked in at 64,154 RPM, regardless of the conditions. But look at how the demands on the system change the other numbers. On a standard 15 degrees Celsius day at sea level with bleed air flowing, the exhaust gas temperature, or EGT, sits at 677 degrees, burning 108 kilograms of fuel per hour. Now look at that second row. Even on a much hotter day at 39 degrees Celsius, if you turn the bleed air off, the EGT plummets down to 364 degrees, and fuel flow gets cut in half to 52 kilograms per hour. It just goes to show how much the mechanical load of providing bleed air dramatically impacts how hard that APU is working. Section 4. The APU bleed air system. Let's talk pneumatic power. When the APU is up and running, pushing the bleed air switch light on the control panel opens the bleed air valve. This air does two main jobs. It supplies the environmental control system, or ECS, and it holds the cabin pressure control system aft safety valve open. But here's where the FADEC logic gets really fascinating. It actively prevents a clash of air sources. If either main engine bleed air toggle switch is turned on, the APU bleed air switch light is automatically de-energized. You literally cannot supply bleed air from the engines and the APU at the same time. On top of that, if the APU exhaust temperature gets too high, the system will automatically reduce the bleed air supply. It inherently gives the APU generator's electrical load priority over the pneumatic bleed air demand. Section 5. The Automatic Fire Protection System. Since the APU sits in its own separate compartment outside the pressurized fuselage, it relies on a dedicated, fully automatic detection and extinguishing system. It monitors the hot section and exhaust using a loop sensor. Now, pilots verify this is working using a strict testing sequence on the Overhead Fire Protection Panel, or FPP. Picture a pilot's finger pushing and holding the momentary action Fire Test Push button. First, you push and hold it to verify all the red and amber warning lights, including the master warning, flash or illuminate. A great memory aid for this step is Hold for the Christmas Tree. Pushing and holding lights up the entire panel to prove all the warnings work. Next, picture releasing that button, and the green fuel valve open light illuminates. Releasing verifies the circuit completes. Your memory aid here, release to green. Letting go gives you the green light that the system is armed and ready. Now, if a fire actually occurs, the automatic response is absolute. Imagine the Q400 tail cone with the APU hot section loop sensor glowing red. When that sensor detects a fire, the APU automatically and immediately shuts down. Think of it as first sight, flight ends. At the very first sign of fire, the APU stops running. Then, picture a countdown timer right over the stainless steel fire extinguisher bottle in the tail cone. Exactly 7 seconds after a fire is detected, the extinguishing agent automatically releases into the compartment. The memory trick? 7 seconds to save. That 7 seconds is the precise, unyielding delay before the automatic rescue kicks in. Finally, Section 6, Faults and Normal Shutdown. As we've seen, the FADEC system is incredibly self-protecting. If it detects a fault, it isolates and shuts down the APU. And the monitoring is totally comprehensive. It looks for overspeed, underspeed, start failures, and acceleration failures. It watches for EGT overtemperature, low oil pressure, or high oil temperature. It even monitors for failed sensors, failed valves, relay issues, and internal failures. If absolutely any of these trigger, the APU shuts down, the fail segment illuminates in amber, the fuel valve closes, and the APU caution light comes on.
But what if you just want to turn it off normally? Well, there's a strict 3-step sequence dictated by the manual. Let's look at the APU control panel. The very first step is securing the pneumatic air by pushing the BL air switch light to close the bleed air valve. Your memory aid? B for bleed air closed. Next, you have to remove the electrical load by pushing the gen switch light, taking the starter generator offline. That's G for gen off. Finally, you push the PWR switch light, causing the run segment to go out and closing the fuel valve, completely stopping the APU. P for power pushed. So, to remember the exact sequence, B, G, P.
Okay, we've covered the mechanical anatomy, the digital brain, the fluid lifeblood, and the strict safety sequences. But I want to leave you with one final thought directly tied to the system's logic. As we learned earlier, the APU system will automatically prevent APU generator output if external AC or DC power is applied to the airplane. So why does the APU generator automatically lock itself out the precise moment external power is introduced? Think back to the electrical bus architecture we examined today and how preventing a simultaneous power clash absolutely protects the entire aircraft's delicate avionics. Understanding that single lockout feature unlocks a much deeper appreciation for the meticulous engineering of the Bombardier Q400. Thank you so much for joining me for this explainer, and keep learning.